In this video lecture, we're going to keep talking about Fourier's law, but now we're going to focus on radial systems. So there are different types of coordinate systems. Last time we talked about Cartesian coordinate systems where our temperature profile was given in terms of x, y, and z. But now we're going to be talking about what if our temperature profile is given in terms of r, phi, and z. So this is called a cylindrical coordinate system. And basically what this is a diagram of a cylindrical coordinate system kind of shown and how that fits in with a more intuitive XYZ coordinate system. So in a cylindrical coordinate system, instead of measuring how far you are in the x direction or y direction, you would measure how far you are in terms of absolute distance away from the origin. So we have this dimension r here. So in the r dimension, that just tells us how far are we away from the xy origin. So then in order to go in different directions, we would use this phi. So phi tells us how far we are away from one particular part, let's say a projection onto the x coordinate. So if we are phi is an angle. So we could express, just like in the xy coordinate system, we could express anywhere on this two-dimensional plane in terms of just r and phi. So how far are we away from the origin, and then how far in terms of degrees are we away from that x vector, and we could still get to any point. We would just have to measure that in terms of our distance from the origin, and then what's that angle like. Then the z direction tells us how far we are axially away from the xyz origin, so how far are we away from that 2D plane in this direction. This will become a lot more intuitive and make a lot more sense once you start thinking about actual engineering systems, and frequently in heat transfer, cylindrical coordinate systems are actually much more convenient and much easier to understand than an XYZ coordinate system, because we have things like pipes, which are cylindrical in shape, or tubes, or nuclear fuel rods. So those types of systems have a natural symmetry if you're looking at it in terms of this r than you would by looking at it in terms of x and y. So let's look at some systems. Oh, and I want to specify there's a little quirk. So Fourier's law, remember, is that the flux is proportional to minus k times the temperature gradient. Well, you have to define that temperature gradient a little bit differently. So remember, a component in temperature is, the derivative of temperature with respect to a spatial coordinate, like when we looked at dt dx, this is a change in temperature divided by a change in distance. So that gets a little tricky when you're talking about this angular coordinate phi here, because an angle is an angle, it's not a distance. So for example, if you're looking at phi here, well, that's going to be a much shorter distance than if you're looking at phi here, so it doesn't make sense to express something just in terms of d phi. You'd want to express it in terms of the arc length here. So if this were the arc length going from here to here, so that arc length ds would be equal to r, or the radius, times d phi. So Fourier's law tells us that the heat flow is proportional to the change in temperature over the change in distance, so it would be cheating to look at change in temperature over change in angle, because that angle could imply a totally different physical distance depending on how you're measuring that angle. So that's where we pick up this r term in the denominator here of our angular change term. So that's something that's important to remember. It makes physical sense once you think about it like this. So it's really like the change in temperature with respect to the change in arc length. But to get that back into terms of our coordinate system, we do change in temperature divided by where you are radially in your coordinate system by phi. So don't be freaked out by this term. It just shows up because you can't measure a distance with an angle. All right, so often in cylindrical systems, we're using this cylindrical system because it makes a little bit more sense to use them. So you might have a nuclear fuel rod, for example, that's going to generate heat, and they're cylindrical, so they're going to generate heat, and then that heat is going to dissipate outward. So if there's no real reason to think that the temperature would vary in the z direction, well, that just becomes a one-dimensional system, just like we talked about with x and y, where temperature only varies with respect to either x or y. It makes the math easier to just calculate derivatives in one dimension rather than in two or three. So if you notice, this particular cylindrical rod, there's no temperature variation in the z direction. There's only temperature variation in the r direction. And then if you wanted to measure temperature variation in that angular direction, that would be going like this. So if we plotted what phi looks like directionally on here, you can see there's no temperature variation. It's going to be the same going out radially, but it's not going to change if you go in the phi direction. So basically, if we were to calculate the derivative of temperature, if there's no temperature change in the phi direction, that term just goes away. And if there's no temperature change in the z direction, then that term just goes away. So we end up with just this one term that our flux only varies with respect to temperature change in the r direction. So this is really mathematically convenient to just be dealing with this single term. Another way we can do this is if, well, what if we have a fluid inside of a pipe or something and that fluid is really well mixed, so there's no temperature variation in the r direction and only in the z direction. Maybe this is a pipe that is being cooled gradually as the fluid flows through it. So in this particular case, there's no temperature variation in the r direction and no temperature variation in the phi direction. So we can nix both of those terms and just look at temperature variation in the z direction. And actually this ends up looking a lot like a Cartesian coordinate system, except we just have this circular cross-sectional area through which heat is going. So this will start to make more sense as we start to solve actual problems, but it's just don't be afraid of these fancier coordinate systems. They actually end up making your life much, much easier. So if we were to look at such a system, in our previous video we showed this exact same plot, except we had x and y. Well, now we're going to show the exact same plot. Remember that t is a function of x, y equals x squared plus y squared. Well, because that system is just the equation of a bunch of concentric circles, it actually is really convenient to express that same exact temperature distribution in terms of radius. And if you'll note, what took us 2 coordinates before to describe now only takes us 1 coordinate. So now we can just say t of r equals r squared, and using that information we can actually generate the same exact plot that we had before. But our coordinate system is different. Now we're going to measure r going out from the origin here, but r being, let's say, if r is equal to 2, or let's say r is equal to 4, well, that could be this direction, that could be this direction, that could be this direction, that could really be any direction r equals 4. But you notice because of the nice symmetry of this system, it doesn't matter. It's the same in any direction. So we're just measuring how far are we away from the origin. If we saw temperature variations going in the phi direction, then we would need to include a phi coordinate, and there would need to be a phi dependence on temperature in our temperature profile if we were to extract any good information on heat flux in the phi direction. So let's look at that, basically the same problem we were looking at before. We have t equals r squared, so now let's look at the point r equals 6. So again, that could be, let's see, 2, 4, 6, that could be out to here, that could be out to here, it doesn't matter. In our previous example we looked at the point x equals -6 and y equals 0. Well, that is exactly the same point here, r equals 6. So let's calculate the heat flux here. So if we look at the definition of heat flux, which is when it's spelled out, we see that there's no temperature variation with respect to phi. Temperature doesn't change at a fixed r. Temperature doesn't change as you go angularly in this direction. So we can just get rid of that term entirely. So the z direction in this particular case would be going in and out of the screen. This would be equivalent to the z direction in the Cartesian coordinate system. So there's no change there, and we know that just because our temperature profile equation doesn't have a z component. So this term is going to be 0. We're assuming that temperature doesn't change as you go in and out of your screen. It only changes in this direction. So if you go out radially, the further you go out, yes, temperature does in fact change, and it increases with respect to radius squared. So if we want to calculate the flux at this red dot, so we have QR is equal to minus k dt dr, and we were going to use a k of 1 watt per meter Kelvin, just like we did in the previous video. Our dt dr is equal to 2 times r, so we get minus k, and then we get 2r. R is equal to 6, so we get minus k times 12. So we end up with a heat flux of minus 12 watts per meter squared. So this is where there's a difference. So before, when we calculated heat flux using our Cartesian coordinate system, we got a positive 12. So remember, x was increasing in this direction, and so our heat flux was going with x. Now, r is going out this direction. We're always going out. So heat flows against our coordinate system, which is what that negative sign tells us. So we get the same vector, except it has a negative sign because our coordinate system is different. So if we're going from out here toward the center, we're actually going against r. So this negative 12 just means we're going inward rather than outward, but we'd actually get the same thing if we did r equals 6 over here. Again, it's the same coordinate in our cylindrical coordinate system. We'd get that our heat flux is going this way. So the physics is the same, what's actually physically happening is the same, but our coordinate system is different, so we get a different sign on our flux vector. But this would still have a magnitude of 12 watts per meter squared. We just know that it's going against r, which means it's going closer to the origin rather than further away from the origin, which increasing r would tell us. Okay, I hope this is all making sense to you. Let's look at spherical coordinates now. So spherical coordinates are even more complicated because, so in spherical coordinates you would use r to measure how far you are away from the xyz origin. Then you'd use phi to measure how far you are away from this x-plane. Then you'd need to use another angle, theta, to measure how far you are away from either the x or the z, and the book's convention is to use z. So we're theta degrees away from the z vector. So again, this gets more complicated. So this is just like if you think about latitude and longitude. So like for the Earth is a spherical system naturally, so r would tell us what's our elevation, or how far are we away from the center of the Earth. I guess that'd be elevation plus the radius of the Earth. But then our latitude and longitude would be really important. So this is just telling us where are we in terms of where are we on the Earth's surface. Then r tells us how far we are away from the very center core of the Earth. So when we look at the temperature gradient, we pick up the same term. This is just like in cylindrical, but then with phi, because we're dealing with a projection onto that xy plane, we pick up this other sine theta term. So again, this is nothing to be, if you went back and did the geometry, you could derive this term. In this class, we actually won't worry too much. We'll use spherical systems a lot, but we'll typically be dealing with systems where we have no variation in terms of theta and no variation in terms of phi. So we'll just be looking at how is our temperature changing and how is our flux changing as a function of r. And that's where you'll see just a ton of value in using a spherical coordinate system, because describing something like that in Cartesian coordinates would be really extremely difficult. So here are a couple of examples. So here's the only picture I could really find of this. So here's the Earth. So temperature is definitely going to vary. At the center of the Earth, it's very hot. And as you go outward, that temperature is going to change. But you really wouldn't expect huge changes in terms of, at least beneath the crust of the Earth, you wouldn't expect huge changes depending on where you are, latitude and longitude wise. So put it a little differently, if we looked at a spherical system, this is a spherical system. Imagine that that's a sphere. This is a spherical system where temperature is only varying with how far you are away. And it's not varying in this direction, which would be theta, and it's also not varying in the direction, I wish I were in person, of coming in and out of the screen. angularly, it's only varying in the r direction, so we can effectively model these systems as a 1D spherical system. And this can be important when you have like a spherical vessel, so you might have a reactor that is spherical in shape that's generating heat, and you need to know how heat is going outward from through the walls of that reactor. You can also have certainly a lot of spherical systems when you're dealing with packed bed systems, where you might have spheres that are in a system in this kind of ball form. So spherical systems are important. Okay, we've talked about how to calculate heat flux throughout these last two videos, this one and the previous one, and it's really important to remember how do you go from flux to the total rate of heat transfer. So if you remember, we've been talking about flux in terms of watts per meter squared the whole time, and it should be pretty intuitive that if you want to go from a flux or a rate of thermal power per unit area, you would just multiply by the area of a system. So if we had a plane wall system where temperature is only varying in the x direction, we would need to calculate our flux using Fourier's law, and then we'd want to multiply that flux by the area that is normal to the flow of heat. So in this case, that would be if our wall is delta z units tall and delta y units wide, then we would need to multiply our flux in the x direction by delta y and delta z in order to get our total rate of heat transfer, which would be in units of watts. So that's all that means. So in this particular system, we'd be only assuming temperature variation in the x direction. We'd be assuming no temperature variation in the y or the z direction. And so, but it's still, y and z are still important. This is still a three-dimensional physical system, but in terms of heat transfer analysis, we're only looking at one dimension, and then we need to use the length and width to convert from flux to total rate of heat transfer. This gets a little bit trickier with radial systems. So let's say that we have some kind of heat flux going out from here. So we have QR flux going out from the center. Let's say it's going out from the center out radially in all directions. So what's tricky here is if you had the same flow of heat leaving from, let's say you have some kind of heat source in here, well, that heat's going to escape, so that same amount of heat is getting from here to somewhere outside the pipe. So the total rate of heat transfer leaving from here out to here is going to be constant. However, as you can see, as expressed by these concentric circles, that in terms of flux, that amount of heat is encountering a different cross-sectional area as it goes outward, or a different area normal to the flow of heat transfer. So our flux, if our flow of heat from here out to somewhere out here is constant, our flux is going to be diminishing gradually the further out we go. So that area is changing as a function of r. So the heat flux here, as measured by this inner circle, would be different than the heat flux here, as measured by that circle, because the heat is gradually dissipating as it goes outward. So all we would need to do is think about what does this area mean. So that area is going to be a function of our radius. So we're looking at the perimeter of our system, 2 times pi times the radius, multiplied by the length of our system. So the length would just be how long is the pipe. And if you notice, this isn't a constant, because r is going to be increasing the further out you go. So too will this area normal to the flow of heat be increasing the further out you go. So it's really important to remember this, because you may be asked to calculate flux here, or you may be asked to calculate the total flow of heat here versus here. So you need to be able to go between flux and area, but note that that area normal to the flow of heat transfer is going to be continuously changing. And again, this is the type of thing that you'll need to study and do practice problems on, and over time with repetition and hard work, this will gradually sink in and it won't be that difficult of a concept. Another term that we defined in the first lecture is the heat rate, the flow of heat per unit length. So when you're dealing with a really long pipe, for example, it might be easier to do your analysis. Let's say you have to analyze some pipeline that is 100 miles long. Well, instead of considering the whole 100 miles, you might just consider a basis of 1 meter. And you could do this heat transfer analysis. Okay, how much heat is my pipe losing per meter? In that case, to get the total rate of heat loss or heat transfer per unit length, which would be in terms of watts per meter, you would just take the flux, watts per meter squared, multiplied by the perimeter, or this 2 pi r, and then you would end up with watts per meter when you do the unit analysis. So that's what the perimeter looks like, it's just 2 pi r. And a way to think of that is just how much heat is being transferred per unit length. So it would just be this guy divided by this guy to give you heat transfer per unit length. So this is more of a housekeeping or definition thing. It's not too difficult of a concept, but this can be a handy little trick to make some of the problems easier to think about conceptually. So for spherical systems, so imagine, I know this looks a lot like the cylindrical system, but I'm dealing with a two-dimensional presentation system here. So imagine this is a spherical system now. So again, let's say we have some generation happening right at the center of this guy. So that heat is all going to need to get out somehow. So heat is going to be traveling from here to some point outside, and the total rate of heat transfer from here out to this outer ring may be constant, but the flux, as the flux goes out, that energy is going to be encountering more and more surface area, or more and more area normal to the flow of heat transfer the further out it goes. So your flux will gradually dissipate because it's the same amount of energy, but it's being dissipated over a bigger area. And that shows up just by looking at the surface area of a sphere, which is defined as 4 pi r squared. So the bigger r gets, the bigger this area will get, and it'll be quadratically proportional to the radius. So just an important definition if you want to go from flux to total rate of heat transfer. So if you knew the flux at this particular point, well, then you would need to multiply that by the total area at that particular point, which would represent this area of this concentric ring, to get the total rate of heat transfer.